Hello everyone, welcome to this presentation. The title of this presentation is Memory Controlled Sequential Self-Attention for Sound Recognition. I am Arjun. I am a second year PhD at QMUL University of London. This work is jointly done with Helen, Vinod and Emmanuel. As an outline of this presentation, firstly, I will introduce my research area of sound event detection and also the objective of this work. Then I will talk briefly about self-attention in natural language processing, especially why self-attention has evolved in NLP and what are the benefits of self-attention. Then I will discuss about the challenges that we faced to apply self-attention functions originally proposed in NLP for sound recognition. Then I will explain our memory-controlled sequential self-attention for sound recognition, which is actually the main contribution of this work. Then I will explain our experimental design, observations, and future work. Okay, so a sound event sequence is an audio sequence composed of different sound events. And sound event detection is the task of predicting sound event labels with corresponding onset and offset timestamps. As you can see from the block diagram, given an input audio representation to the SCD model, these are the predicted sound event labels by the model with corresponding onset and offset locations. The objective of this work is the design of self-attention functions for improved sound recognition. Let's discuss in brief about self-attention in natural language processing. We all know that recurrent neural networks are the standard functions used in time series problem. However, RNNs have a few drawbacks. Most importantly, RNNs lack a mechanism to learn the relations within a sequence. For example, here in the given text, Arjun is wearing a red shirt. The word wearing is differently related to other words in the text, but RNN doesn't have an explicit mechanism to quantify or to learn these recurrence relations within a sequence. And self-attention functions are actually evolved to overcome this limitation of RNN. Equation 1 represents the general form of a self-attention function. Here HT is a latent feature representation. HT tilde is the attention weighted feature. Alpha i's over T are the attention weights for the current frame HT. Now imagine I apply self-attention function to get a better representation for the word wearing. In this particular example, we could expect alpha shirt over wearing to have the highest attention weight value because of the semantic relation inherited in this text, followed by alpha Arjun over wearing and like that. So in this way, self-attention provides a better summarization of the input sequence. This is actually supported by the semantic and structural relations inherited in text. Now, what are the challenges to apply self-attention functions to sound recognition? Imagine I have an audio input sequence having different sound events from E1 to E5 like this. And I apply self-attention function on my sound event E3 to get a better representation of the same. Basically, now the function will look at relations between E3 and other sound events in this audio input sequence. But here the biggest question is, are there any meaningful relations between these pairs of sound events in an sound event sequence? I think it's hard to say yes, because sound event sequences lack semantic and structural relations. So this is one of the challenges that we face to directly implement self-attention function to sound recognition. The second challenge is that in reality, I don't have these event-based representations in sound recognition problems. Rather, the event-based representations are divided into small snippets of audio that we call by audio frames. Now the self-attention function is actually applied on top of these temporal frames. But Basically, now the self-attention is simply based on the pairwise frame level similarity computation. In this context, it is highly likely that this particular frame is wrongly summarized as a frame from this event E1 by the self-attention computation. In this manner, this way of self-attention implementation on frame level features will cause the recognition performance and generalizability of sound recognition model. Now, we propose memory-controlled self-attention to overcome this limitation. So we put two strong assumptions. First of all, recurrence relations are uncertain in sound event sequences. However, there exist temporal relations between audio frames within sound events, and we can effectively model these relations using a constrained self-attention function that we call by the name memory-controlled self-attention. Basically, it applies a constrained self-attention to a neighborhood related to each frame level encoding, with L being the attention width. So, for example, in this figure, to compute an attention representation for this particular frame, now attention function is constrained to a neighborhood of L frames, like L by 2 to the right and L by 2 to the left of the current frame. And equation 2 is a memory controlled attention representation. Now, let's discuss the multi-head memory controlled self-attention design. A limitation of the memory controlled self-attention function in equation 2 is that it always uses a fixed attention width value to summarize each audio frame in a sound event sequence. But this is not an optimal design because every sound event sequence has different sound events, also with different durations. So in order to overcome this limitation, we design a multi-head memory controlled self-attention function. Here, we choose a set of attention width values. Then for each attention width value, we computed a memory controlled self-attention function. Similarly, we have different attention head values, and the features from different attention heads are concatenated and a normalized weighted sum is computed, which will give the final attention-based feature representation. Here, WAH is a trainable parameter. These weights are shared across all the attention heads. We use standard representation of query, key, and value notations to represent the multi-head self-attention function in equation 3. In this work, we empirically choose the number of attention heads to be 11. And in the first attention head, we keep L is equal to 2 as attention width. And in the subsequent attention heads, we serially increment L by 5 friends, which means in the second attention head, the attention width value is L is equal to 7. And our experimental details, we use Urban SCD dataset, which is publicly available, having 10,000 different soundscape with 10 different sound events and coming in polyphonic structure. Our SCD model is based on convolutional recurrent neural network architecture. That is a baseline model. Then we implement self-attention function on top of the CRNN model. And we also have a final multi-head memory controlled self-attention model. Our models are evaluated using F-score and error rate, both based on segment and event-based manner, with event-based F-score as our primary metric. Figure A shows the block diagram or architecture of our SCD model. Input to the model is a magnitude MEL spectrogram, which is given to the CRNN block. CRNN block contains 3 convolution layers and a single GRU layer. Self-attention function is implemented on top of the CRNN block, and then there is a finite prediction layer. Figure B shows the block diagram of our multi-head self-attention design. So the weights are actually shared across all the attention heads, and the query is also the same. For each head has corresponding key and attention sets based on corresponding attention with values. Now the attention features from each of the attention head values are concatenated and a normalized weighted sum is computed, which will give the final attention feature. These are the results. Baseline model represents the baseline CRN and SCD model. Self-attention is a self-attention based SCD model without any memory control. Self-attention underscore L is the self-attention based SCD model with memory control with corresponding attention with value. And multi-head represents a multi-head memory controlled self-attention model. Here we can see that the self-attention model without memory control is very poor compared with the baseline model, which will actually verify the need for a memory controlled self-attention in case of sound recognition. And the best results are actually obtained with self-attention model with attention with the value 50 frames. We expected a similar performance or a better performance with the multi-head design, but in this work, the multi-head design is not really optimal. The bottom figure shows the event-based F-score values for individual sound events. Here also, except for the sound event car horn, for all the other sound events, the best performance is obtained using the self-attention model with attention width of 50 frames. So these are the conclusions from our work. Memory controlled self-attention is an effective approach for sound event sequence modeling, which will actually improve the recognition performance. Multi-head memory controlled self-attention design in this work is actually not optimal. So this is actually one of our straightforward future goal to have an optimal design of the multi-head memory controlled self-attention. We also look forward to verify the effectiveness of memory controlled self-attention for sound recognition on other dataset. We also look forward to have a detailed analysis or a mapping based on recurrence relations happening in a sound event sequence with the corresponding attention with the values. We also look forward to use the benefits of memory controlled self-attention model for sound sequence generation, like to create sound event-based encodings, and also use these models as a pre-trained model to compute other relative tasks. We also look forward to verify the effectiveness of memory-controlled self-attention for relative tasks like urban sound tagging and acoustic scene classification. Thank you very much. If you have any feedback or if you have any questions, please feel free to contact me on my email, which is provided at the title slide. Thank you very much.